In this example, we are given the half-life of radium, and we are then told another scenario about this same element, radium. So really here, what we have are two parts to this overall question. Now, it is an exponential decay model. We do know that these elements decay in this way. So one of the things that we could do is ask ourselves, what do we know? What do we not know? And in the issue of half-life, if we know that half is going to be present, it doesn't matter, actually, it doesn't matter here what the initial and the output value would be for that half-life. We just know it's going to be at a ratio of half. So those things are actually known. We can consider them as okay, we have values here. And we also have that value T for the half-life. We know that it takes 1,690 years. So using just this one number, we can find for our missing piece of our model, K. Okay, so let's do that part first, just with that one number. So again, it doesn't really matter what the initial value is. I could say that the initial value here, let me fill in some parts of this at least. I could say that the initial value is 100. Then I would know after 1,690 years, what is left is half. I could say that the initial value is 200, and after 1,690 years, what is left is 1/2 of that, or half of that. Or I could say what the initial value is 1, and what's left after 1,690 years is 0.5. So anyway, no matter what I pick here for initial value, there will be this relationship between these two pieces, given that the half-life is, we know this half-life, we know that time. So that allows us to solve for K. So since K is in the exponent, that means I need to change this to a logarithmic form. That is the inverse of an exponential form, is the logarithmic form. And then divide both sides by this 1690, and that will solve for K. Using my TI calculator, I just type that in and I get this output value on my screen. And actually this is a really small number. I need to remember that E, -4, is a shorthand for scientific notation. So if I change this to a standard form, it would look like this. Now you might ask, well, why am I keeping all these digits? Do not round until the final answer. So another thing that I could do in my calculator is either store this value as K, or I could just refer to it as the previous answer as long as the next line is what I do something with this number. Okay, so the next thing that we want to do is set up the scenario given here, that if 60 grams are present, how much will be present, or present now, how much will be present in 570 years? Now, just really quick, think about that. 570 years, would we expect 30 grams? Would we expect half? Less than half? Or more than half? Well, because it's 570 years and the half-life takes 1,690 years, we shouldn't see half or less than half. We should have more than half present of the 60 grams. So that's just one way to kind of check your reasonableness of your answer as you go through this scratch work. All right, so again, I don't know this output, but I do know that it's going to take 570 years. 60 grams are present right now. I do have this value of K, which I need to keep all of those digits for accuracy, or just refer to it as previous answer in my calculator. And again, I know the time is 570. So this one's a little bit more straightforward because I have the input. I can just type this exact expression into my calculator and then round to the thousandths place. And that's how we arrive at 47-ish grams. And notice again, that is at least more than half of the 60 grams. That's more than 30. So that goes in with the reasonableness of our answer, what we were expecting.